Hello everyone, I'm Deepam Goswami. I will be presenting our paper which has been accepted at the CoLLAs 2025 conference. Our paper is on query drift compensation, enabling compatibility in continual learning of retrieval embedding models. This is a joint work with Ling Wang, Bartholomew Twardowski, and Joost van de Wever. So we are interested in continually learning embedding models which could be used for document retrieval. For example, we have some data sets over here which covers different domains, which has been taken from the BEIR benchmark, which is a very well-known benchmark used for document retrieval. And we have queries which can be given by users, and then we have documents which is extracted from the huge corpus of millions of documents from each of these data sets. So the task what we want to do is document retrieval. For each query we want to find the document from the corpus which is closest to this question. And what we have at training time is we have access to the query and document pairs, which is the part of the training data. And what we are interested in doing in our paper is like we want to continually perform document retrieval. So for instance, here we establish a benchmark for continual document retrieval to see how continual learning works on these large scale datasets. And we use these 5 datasets from the BEIR benchmark, and we sequentially fine tune the embedding model in a supervised contrastive manner using the query document pairs from the training set. And then we see how the model performs on the new and old tasks. So, document retrieval, when we want to learn continually, these models could be done. One way of doing is with re-indexing. For instance, if you have a model F1 trained on your task 1, and we embed the corpus, the documents in the corpus of this task into a embedding index. So for every document in the corpus, we have a embedding vector in the index, and then we update the model from F1 to F2 using the training pairs, the query document pairs from the task 2. And what we will do is we ideally need to embed the documents from the corpus of task 2 uh, to the embedding index of this particular task. Now, one way of doing continual document retrieval is with re-indexing. So what we can do is we can re-index the corpus, the documents from the corpus 1 to have the updated set of embeddings for those documents, because the model has changed from F1 to F2, and this set of embeddings are not valid anymore to be used with this model F2. And then what we have at retrieval time is we, even though the query is from the old task, it has to be passed to the current model because we have the final model at a time. And then we have this query embeddings which we search in the re-indexed embeddings, corpus embeddings from the old task and the current task here. So this is one way. However, this approach is a very expensive approach because imagine after 100 tasks, you have to re-index millions of documents from each of these old tasks to update their embeddings and make sure that the document embeddings are in the updated embedding space, which is compatible to the query embeddings, which is passed through the updated model. So in order to avoid this whole re-indexing process, what we propose is a re-indexing free continual document retrieval approach, where we do not need to perform re-indexing. We can still use the old indexed document embeddings. And how we do it is we propose this query drift compensation method. So at retrieval time, when you pass the query from the old task through the updated model, you get this query embedding in the updated embedding space, and we do a backward projection to the old embedding space of that particular task. So what how we do it is we measure we just do a query drift compensation. So we subtract the drift vector which we had estimated before, and so that the query embedding ends up in the old embedding space, which is then compatible with these embeddings which have been indexed using the old model, so that we do not have to do the re-indexing. So how we do the query drift compensation is we pass the query at time from the current task. So we assume that the drift of the queries of the current task is going to be similar to the drift of the queries of previous tasks. And we see that this assumption holds quite well. So we pass the query embedding through the old model and the new model. We obtain the positions of the embeddings, and we just measure the drift and store this drift vector. So for every task transition, we have one drift vector. And at retrieval time, we pass the query from the old model, which could be from a T prime task, an old task, and we get these embeddings, and we do the we take the corresponding drift vector to project it to the old task from T to T prime by subtracting the corresponding cumulative drift vector, which is just an addition of the drift vectors from all tasks for all tasks starting from T prime to T. So this is a very simple drift subtraction method, and it's this drift is just computed during every task transition, and one drift vector is stored per task. And how does it perform? So if we start with the experiment, so we propose this benchmark with 5 datasets, which covers different domains and different types of tasks. Which has like we select these datasets which has sufficient training pairs, and then at test time we have these queries and a lot of corpus like 57,000 to 8 million documents to perform retrieval. And so we use this sequence of T1 to T5, and we compare with a naive fine tuning, contrastive fine tuning, and we see that there is quite a bit of forgetting. We have the joint training upper bound over here, and then we perform query drift compensation along with fine tuning, which improves significantly compared to fine tuning. And then we also propose just a knowledge distillation on the query and corpus embeddings between the old and the current task. And we see that knowledge distillation also helps, and we get a much better average score, which is pretty close, which is same as the joint training. And we also have an interesting observation that when we actually perform re-indexing, we do not get very good satisfactory results. And we talk about that in the paper also. So we have this analysis in our paper where we see that so if you look at this UMAP visualization, we have the first data set MS Marco, and then we take the and we notice how these documents and the queries of this particular dataset MS Marco drift after training on task 2 and task 3. So we see that the MS Marco documents has moved from this green patch to this red patch, which is much significant drift. And we see that the query embeddings of of the same dataset has moved much less, significantly less compared to the documents. And we find a correlation between like why this phenomenon is happening, that the the drift of the query and the documents actually is dependent on how long is the length of the query and the documents, which means that the more information a document or a query has, it experiences higher drift, which is kind of intuitive. So we see that we divide the query and the corpus into 3 segments of short based on lengths, short, medium, and long, and we see that in queries also, like the drift average drift increases, and in corpus we see even the same phenomenon. With length it increases, but in general the corpus experiences much higher drift compared to the queries, because if you look at this table over here, we see that the average length of queries are much smaller, while the average length of documents are much longer. So basically the documents which has much more information drifts more compared to the queries, resulting in in a non-compatible embedding space, which is the reason why re-indexing does not work very well. Uh, so that's it. If you are more interested in things in the paper, feel free to read our paper. Thank you.